Hello everyone, I am Ritika Juswar, Assistant Professor IT Department. So in the course of Unit 3, in previous video we discussed about the fuzzy logic or a concept of fuzzy logic, then fuzzy logic architecture also. So in this video we will discuss about the fuzzy operations. So what are the operations are performed in the fuzzy logic. So before starting the operations of fuzzy logic, first we discuss about the basic definitions and terminologies used in the fuzzy logic system. Okay, so let us discuss here.
What are the basic definitions and terminologies used in a fuzzy system? Okay, so the first is a fuzzy number. A fuzzy number is a fuzzy subset of the universe of a numerical number that satisfies condition of normality and convexity. It is the basic type of a fuzzy set. So why we used a fuzzy? And why we will learning about fuzzy? And the word, the fuzzy means that in general sense, when we talk about the real world or expression of the real world, the way we quantify the real world and the way we describe the real world are not very precise. When I ask what your height is, nobody would say or nobody would expect you to know a precise answer. Okay, so we don't find out easily what is a height. Okay, height value. So if I ask a precise questions, probably you will give me your height as a 5 feet 8 inch, okay, and another some height value, okay. But normally when I see people, I would say this person is tall according to my own estimate, okay. So we are not easily find out the uh, person having what is the height for that particular person. So we only know the person is a tall according to the our own estimation. So my own belief and my own experience, or if I ask what the temperature is today, so the normal answer people would give is today is very hot or a cool, okay. So our expression about the world around us is always not a precise answer. Okay. So not to the precise is exactly what is a fuzzy. So the fuzzy logic is a logic which is not very precise. We are not find out the proper answer for that particular problem. Okay, real world problem. Since we deal with our world with this imprecise way. Okay, so naturally the computation that involves the logic of impreciseness is much more powerful than the computation that is being carried through a precise manner, or rather precise logic based computation is inferior. Not always, but in many applications they are very inferior in terms of technology applications in our day-to-day benefits. So the normal way a fuzzy means from precise to imprecise. Here, when I say 10, I have arrow at the 10 pointing. Okay, so that I am exactly meaning 10 means 10.000 and so on, very precise. So when I say they are almost 10, so I do not mean only 10, rather than in the peripheral 10 dot. Okay, so I can tolerate a band from -9 to 9. Whereas if I go towards 9 to 11, so I am going away from the 10. Okay, 9 to 11 means going away from the 10. So the notion of the 10, that is what is almost 10. So that is around the 10, but in small bandwidth, I still allow the certain bandwidth for the 10 value. So this concept to be imprecise is a fuzzy, or to deal with the day-to-day data that we collect, all we encounter and representing them in an imprecise manner. Like here, almost zero, near zero, or hot, cold. Okay, so if I am referring to height, tall, height is a tall, short, or medium. So this kind of terminology that we normally talk or exchange among ourselves in our communication actually deals with the imprecise data rather than the precise data. So the naturally our communication are imprecise if you are talking about height for the particular person, okay, or if you are talking about the what is the today's temperature, so we are not getting the we are not find out the proper answer, okay. So so uh, uh, the today, so in our communication actually we are deals with the imprecise data rather than the precise data, okay. So the our communications are imprecise. So the computation resulting out of such communication language, so the language which is imprecise must be associated with some logic. So based on some logic, we are find out or we are getting the answer. The person is a tall, okay, or a short, or a medium, or the today's temperature is this. Okay. So this is only just a imprecise data, or we can say that some logical data. So in this diagram, so the figure shows the set. This is a set for classical and fuzzy boundary. Okay. So here the mu of x is a membership value and x is a set. Okay. Set of x. So here the classical crypt set A and fuzzy set A. So this line, blur line shows that this is the crypts set A, and the this line shows that dark line shows that this is a fuzzy set A. Okay, and this is the membership function mu of x. The membership function goes from 0, okay, to 1 and then decreases. So the second terminology is a set. Okay, so this is our set for the classical set and fuzzy set. So what is a set? A collection of objects having one or more common characteristics. Okay. For example, set of natural number, set of real numbers, members or elements. So this is these are the set. Okay. Here also a collection of objects having one or more common characters called as a set. So object belonging to a set is represented as X belonging to a where A is a set. So here object belongs to a set is represented as a X. It belongs to the set A where A is a set. Then what is the universe of discourse? So they're defined as a collection of object all having the same characteristics is called as a universe of a discourse. So the notation U or X for the universe of discourse the symbol is a U or a X, and the elements in the universe of a discourse are a small u or a small x. Okay. Then the next point is a support. So the support of a fuzzy set A is the set of all the point x in x such that mu of A of x is greater than 0. So here the support of A is a x is a mu of A, that is the membership function value for x is greater than 0. So okay, so this is a support system. Next is a core. So the core of a fuzzy set A is the set of all the point x, small x. Okay. So in capital X, such that mu of A of x is equal to 1. So we are writing the core of A is equal to x set of x mu of A, that is the membership value, is equal to 1. Then the normality of fuzzy set A is normal if its core is a non-empty. So always there is at least one x with the mu of A of x equal to 1, then it is a normal. Next, crossover point. So crossover point in a fuzzy set A is the x with a mu of A equal to 0.5. Okay, so if you are getting the mu of membership value is a 0.5. Okay, if you are getting the some value for the mu of x 0.5, so this is our crossover point. If you are getting the value mu of a of x is equal to 1 for the all the x set, so then the our fuzzy set is a core. Okay. Similarly, for mu of if you are getting the membership value is greater than 0 for equal to 1, here also equal to 1, 0.5, and a normal and convex fuzzy set. Bandwidth means for a normal and convex fuzzy set. Width A equal to x2 minus x1, where x2 and x1 are a crossover point. If you are getting the two crossover point, so then we are find out the bandwidth for that particular set, that is x2 and x1. If here we are getting the width between width A, that is the difference between the x2 and x1, two crossover point difference. Then the fuzzy singleton. So fuzzy set whose support is a single point in X with the mu of A equal to X equal to 1 is called a fuzzy singleton. Okay, so these are the basic terminologies used in a fuzzy system. So the main feature of operations on fuzzy set are that unlike conventional set, operations on fuzzy set are usually described with the reference to a membership function. So when I say the operation, I do not do with the member itself, but I manipulate the operations. So when I say the operations, I manipulate the membership of the member in a set A. So the members are not manipulated, rather the membership function of the member is a manipulated. So this is very important that the x and mu of x. So x is a set and the mu of x is a membership function for the particular set x. So in a classical set, what is a manipulated is a x. So if I say x is a 1 in a classical set, if x has a value equal to 1 in a classical set, so when I say x is a 1, then I would say 1 minus x is a 0. Okay, if the x value is equal to 1, then the 1 minus x is a 0. So in this, the manipulation concerned with the member. Whereas any kind of manipulation in fuzzy set does not involve with the x rather than involve mu of x. So what is the containment or a subset for in a fuzzy system? So the fuzzy set A is a content in a fuzzy set B. Okay. So what are the classical set? In a previous lecture, we discussed the classical set. Okay. If we are having x in the classical set equal to 1, then the answer is 1. And then if the answer x is not belongs to a, that is 1 minus x, then the 1 minus x is a 0. Okay, so this is our simple classical set. And these are the operations performed in a classical set. Okay, uh, union, intersection, complement, difference, and commutativity, associativity, distributivity, and so on. Okay, so here a fuzzy set A is a content in a fuzzy set B. We are generating two set over here. for equivalently A is a subset of B. So A is a subset of B, or A is a smaller than or equal to B. Okay, if and only if mu of A x is also less than or equal to mu of B of x. Okay, if you are getting the A is a subset of B, or then the A is a smaller than or equal to B. If the A set is a less than the set B, then the membership function of mu of A of x is always less than or equal to mu of B for all x. Okay, clear? If we are having the A is a subset of B, so it means that A is a smaller than the B, or A is a subset of B. So in that case, if for a membership function for a set A is always less than or equal to membership value for a B set. So three common operations are performed in a fuzzy set operation. First is the intersection, which we say is the minimum function. Okay, if you are using the two set, okay, and for that particular set, if you are intersecting these two set, so in that case, the minimum function is if in that case we getting the membership function is a minimum. If we are using the union function for a two set, so which we say that the maximum function. If in that case we are getting the membership function is a maximum value. And then the fuzzy complementation. Okay, so in a fuzzy set operation, there are three main common operations performed. First is the intersection. In that we are getting the minimum value. The second one is the union function. Okay, second one is a union function, so where we are getting the maximum value, and third one is a fuzzy complement. Okay, intersection is also called as a conjunction or a T norm. Union is called as a disjunction or a T connorm or a S norm, and third one is a complement, that is negation. So these are the three standard fuzzy operations used in a fuzzy system. Clear? Any doubt up to this? So first is the intersection, that is conjunction or a T-norm. So we can easily see that the membership of a so the membership function is computed minimum, that is mu of A intersection B is a minimum of a mu of A and x and mu of B of x. So that is the membership function. So when there is a common member between A and B, then the membership function whenever is a minimum, that is retained and the other one is a thrown away. So the member is retained, what is changing the membership function. So for the intersection, if you are having the two set A and set B. So for the intersection, there is a common member between A and B. In the intersection, we are find out the common values between A and B. Okay, and for here we are using by using the set A and set B, or by using the intersection for set A and set B, we have to find out the membership function, that is common value from the set A and set B. So we can easily see that the membership of A green, A set A, that is the green, intersection set B. Okay, here green is a set A value. Okay, we are applying the membership function for the A intersection B. Okay, in previous we only getting the set x for the set x. Okay, but in this we have to find out, we have the two set over here, set A and B. So by using this set A and set B, we have to intersect these two set and applying the membership function. Okay, so this is our set A. Green part is a set A and red part is a set B. So the membership of A green intersection B red in this figure, so is all the members that belongs to this common. Okay, so for here the common is that, so blue line. Okay, so this is a common between red and green. So all the members that belongs to that is common between A and B, so their membership we will follow this blue curve. So there are two things we are doing here. We have two set, one is the set A and other is the set B. So the classically what we see is the common members between A and B. So we are not only seeing the common members, so here we are also seeing what is their membership function. Okay, so in a previous lecture we are calculating the membership value for particular set, but here we have to find out the membership value for this intersection point. Okay, that is blue arrow. So here we are also find out what is their membership function for this particular blue line. So this diagram shows the fuzzy set operation intersection, and this is a simple formula for the intersection. So here we are generating one another variable mu of c equal to x, and we have to find out the minimum value. Okay, so intersection, in the intersection which we say is the minimum function. Okay, we have to find out the minimum function for a uh, membership function of A and membership function for B by using the intersection. Okay, so the membership function is computed minimum here, so that is mu of A intersection B is a minimum of mu of x and mu of A of x and mu of A of B of x. Okay, so mu of A is an intersection B is a minimum of mu of A of x and mu of B of x. So that is the membership function. Okay, so this is a final intersection for a membership function. So when there is a common member between A and B, the membership function where is a minimum that is retained, and the other one is a thrown away. So the member is retained. What is changing is the membership function. Okay. So next is a simple example by using the intersection A and B. So here example A equal to set x1, x2, x3, zero point 0.5, zero point 0.1 and zero point 0.4. Okay. Here we are plotting the 0.5, 0.1 and zero point 0.4 for a A. Then for the B, zero point 0.2, zero point 0.3 and zero point 0.5. So we are plotting these values. And for the C intersection A and B, so they are so here we are getting the intersection point, point 2, point 1 and point 4. So intersection points. Okay, and the final intersection mu of A and B is a 0 0.2, 0 0.1 and 0 0.4. Okay, so this is the final diagram. Up to this is a set A, and from this line to this Q, this is a set B, and this is a intersection between set A and set B. So this is the final diagram of a intersection. Here we are getting the A point, X point and Q point. So this is a simple example for the intersection set A and B. So if you are getting the union for a set A and set B, so in that case, so the A and B for the A and B, the membership value is a maximum for both A and B. So if I have common members, so I have set A and I have set B. So A union B is my union set. So if X belongs to A and X belongs to B, so there X also belongs to A union B. So but in a fuzzy set, here the mu of A of X and here the mu of X, and in this case this is the maximum of mu of A of X and mu of B of X. So the membership function. Okay, here we are using the union for this membership value for A and B, and we are getting the max value, and this is our final maximum membership value for a union A and B. So here, so this union set, when it comes to A union B, take these two values of the membership. Find the maximum, which is 0.1, and assign here, which is 0.1. So this is mu union B is a 0.1. Okay. So here the membership value for the set A, blue is a set A for a membership value for a fuzzy set A. Green is a membership function of a fuzzy set B, and membership function for a fuzzy set A union B. So here for the A union B, if we are find out the membership value for A union B, in that case we are getting the maximum value. Okay, so this is our smallest set for A and B, but the membership value for the A union B is a maximum. But in an intersection, if we are having the set A and set B, so the membership value for the set A and set B in the intersection point of view, the value is a minimum. Okay, so this value is a minimum. But in this case, we are getting the rate is a max compared to the set A and set B. So this is very important operation that we perform. So when we have two different fuzzy sets, the operations are classical. So the manipulation is among the membership function. Otherwise, the notion of the classical fuzzy operations also remain intact. And except that the associated fuzzy membership get changed. Okay, so this is the union set A and set B. This is membership function. This is universe of discourse, that is X, and this is a maximum membership function for the set A and set B. Clear? Any doubt up to this? Then this is simple example for this union A and union B. Set A and set B. We are getting the max membership value by using the mu of A and mu of B. So example A union B. Okay, we are plotting the 0.5, 0.1, 0.4, that is green line, and for the set B we are plotting red. Okay, so this is our red. Okay, so in the intersection, this is our diagram, and here also this is our for the union point of view, this is our diagram. But here we are intersecting this value, so the graph is green and red. Okay, and here we are union values. Okay, so this graph is final graph for the union, 0.5, 0.3, and 0.5. Okay, this is our union and this is our intersection. Okay, so here this is intersection. So this part for the A and this part for the B. So here this part belongs to the set A also and set B. Okay, so the region is this. But in a union, so this region is a B region and this region is a region. So whole this region is called as A union B. That is, this is the membership value of mu A. This is the membership value of B, and this whole part is called as A union B. That is membership function for A union B, and this is the intersection. Clear? Any doubt up to this? Yes or no? समझ में आ रहा है पक्का? So the third operation is a complement, that is negation. So now it is a fuzzy complementation. So what is complement? So this one, the particular triangle function is a set R. That is fuzzy set R. Okay, so red region is a we are generating one region that is set R in the red color. So the complement is like this, just inverse of a blue. Okay, if you are getting the inverse uh, graph is like this. Okay, blue arrow, blue line. Okay, so the complement means you inverse of a R. Okay, so this is our R region, and the complement for that particular R region is a blue line. Okay, so the complement is just a inverse. Okay, so the R is our set, and the complement for the R is a R dash. Okay, so this is our inverse, inverse of a R line, red line. Okay, so what is 1 minus mu of A of X? Okay, the if you are having the mu of, if you have to find out the complement for a membership value A bar, so 1 minus mu of A X. Okay, so this is our complement, that is negation. What is seen that the members remains intact in the set A, whereas the associated membership functions got changed. And the example for the complement is, this is our equation 1 minus mu of A of X, and the example 0 0.5, 0 0.1, 0 0.4. Okay, so this is our set A. In a complement we are using only set A, but in a union and intersection we are using the set A and B. So here only we are generating the set A. So this is our 0 0.5, 0 0.1, 0 0.4, similar. Okay. So here also we are using for set these values, in intersection also we are using this value. Okay. So this is our set A, and for the complement, okay. So this is our inverse. Okay. So blue line, the inverse of mu of A is a this line. Okay. Blue line from here top to bottom, and here bottom to top. So this is the inverse of a set A, that is mu of A dash. Thank you.